Respected sir, we the Group 16 are here to present our project on FM demodulation using PLL IC CD4046. This video contains the explanation of design and simulation of FM demodulation circuit using PLL IC CD4046. I am Alaksundan Gogoi and my roll number is EEB15012.
I am Anukul Datta and my roll number is EEB15014.
I am Surajalam Laskar, my roll number is EEB15015.
I am Debanita Das and my roll number is EEB15011. In our report, we have used the term PLL, which stands for phase lock loop. Phase lock loop in its monolithic form has significantly great increased use in digital systems and signal processing such as frequency modulation and demodulation. In our project, we have used CD4046 as the PLL, which consumes 600 microwatt power at 10 kilohertz frequency. Thus, we can see that it is more efficient than any other similar bipolar monolithic PLLs. Now, we are going to continue with the explanation of the PLL system's block diagram.
This is a PLL system basic block diagram. It comprises of comparator, low-pass filter and a voltage control oscillator, which are connected in a closed loop frequency feedback configuration. When there is no input signal to the PLL system, the error voltage at the comparator output is 0, and also the output of the low-pass filter is 0, which causes the VCO to operate at center frequency F0. When an input signal VST is applied to the comparator compares the phase and frequency difference of the input signal and output of the VCO, and the error voltage is filtered by the low-pass filter and applied to the control input of the VCO. The input of the VCO varies in a direction that reduces the frequency difference between VCO and input signal. When the frequency of input signal is sufficiently close to VCO frequency, then the closed loop of the PLL forces the VCO to lock in frequency with the input signal. That means, at lock condition, VCO frequency is identical to the input frequency except for a phase difference. So this is what exactly the PLL IC CD4046 is doing. So let us see how this IC works and its internal configuration.
Here, figure shows a block diagram of the CD4046, which has been implemented on a single monolithic integrated circuit with pin configuration. The PLL structure consists of a low-power linear VCO and two defined phase comparators, having a common signal input amplifier and a common comparator input. A 5.2-volt Zener diode is provided for supply regulation if necessary. The VCO can be connected either directly or through frequency dividers to the comparator input of the phase comparators. The low-pass filter is implemented through external parts. Phase comparator 1 is an exclusive OR network that operates analogously to an overdriven balance mixer. To maximize the lock range, the signal and comparator input frequency must have 50% duty cycle. Phase comparator 1 enables a PLL system to remain in lock despite high amounts of noise in signal input. In order not to load the low-pass filter, a source follower output of the VCO input voltage is provided, that is demodulated output. If this output is used, a load resistor of 10 kΩ or more should be connected from this terminal to ground. If unused, this terminal should be left open. A logic 0 on the inhibit input enables the VCO and the source follower, while a logic 1 turns off the VCO and source follower to minimize standby power consumption. The user must supply a loop filter in a closed loop to operate the PLL. The high input impedance of the 4046 make it easy to select external components. When a PLL is locked on an FM signal, the VCO tracks the instantaneous frequency of the signal. The VCO input voltage, which is the filtered error voltage from the phase detector, corresponds to the demodulated output. Figure shows the connections of the CD4046 as an FM demodulator. The signal must be C coupled to the signal input terminal 14. Phase comparator 1 is used for this application because a PLL system with a center frequency equal to the FM carrier frequency is needed. Phase comparator 1 lends itself to this application also because of its high signal input noise rejection characteristic.
So in this section, we will explain the connections, how this circuit is designed, and we will also explain the output of the simulation and its behaviors. For this, we are using ORCAD Lite version 17.2.16. So let us take a look at the schematic of the circuit. This is the schematic of our project. Here these two ICs are CD4046 whose footprint is of type DIP16. So for demodulation, as we need a modulated signal, we first generate the FM signal using the same IC CD4046 whose input is an AC signal of amplitude 1 volt and frequency 1 kHz. This input signal is fed through a high-pass filter connected pin 9 of the modulating IC. In this high-pass filter, we use capacitor of 1 microfarad and resistor of 10 kilo ohm. A 5 volt DC supply is also connected here through a 10 kilo ohm resistor. We connect pin 5 and 8 to ground, and pin 11 and 12 are grounded through resistor of 10 kilo ohm and 100 kilo ohm respectively. Pin 6 and 7 are connected with a 2 nanofarad capacitor in between, and 5 volt is applied at pin 16. Now pin 14, 4 and 3 are shorted, and remaining pins are left as it is. Now the modulated output we can see at the output of pin 4. So the pin 4 of the first IC is connected to the pin 14 of the second. That is, we connect the modulated output as our input for the demodulating part. In the demodulating part, pin 8 and pin 5 are connected to ground, and pin 3 and 4 are short. Pin 16 connected through a 5 volt DC source. Now here also the pin 6 and 7 are connected with a 2 nanofarad capacitor in between them. Pin 11 and 12 are grounded through 10 kilo ohm and 100 kilo ohm resistors respectively. Here on these two resistors and the capacitor, VCO output frequency is dependent. So we select the values in such a way that the VCO produces pulses which matches the original unmodulated carrier frequency of the FM wave. A low pass filter is connected between pin 2 and 9, whose values are selected in such a way that the time constant should match the range of the frequency at which the message signal is expected. In pin 10, a second order low pass filter is connected with capacitor of 0.01 microfarad and a resistor of 10 kilo ohm. Also 10 kilo ohm resistor is connected at pin 10, which is grounded. At the output of this low pass filter, we connect our probe to see our modulated signal. We have also connected the probes at the input to the modulating IC and the input to the demodulating IC. Now we are going to run this program. Here this is the message input, this is the frequency modulated signal, and this is the demodulating signal. Here we can see that as the input amplitude rises, the frequency of the modulated signal increases, and as the amplitude decreases, the frequency of the modulated signal decreases. We also see that the amplitude of the modulated signal is very low, but even though at the demodulator out, we get the message information. So it is good as to transmit a high amplitude modulated signal. It consumes more power than the low amplitude modulated signal, so efficiency is more. Here the distortion in the demodulated signal is actually due to the log time of VCO out with input to comparator. So if we need the amplitude of modulated signal to be high, then we have to connect a impedance between the modulator output and the modulator input. So when we connect a resistance at the modulator on input and simulate it, we can see that the modulated signal amplitude is high as it draws power. And when we connect a capacitor instead of resistance and simulate it, we can see that now also the modulated signal amplitude is high, but in this case we also see that the VCO locking time is also reduced. So we can say that by coupling the input to the demodulator, we can reduce the VCO locking time with the input frequency.
So from the output of our simulation, when we compare the output of the modulator and the message signal, it is seen that the output of the modulator varies directly with the message signal's amplitude. When the message signal amplitude increases, the modulator of the output frequency increases, and when the message signal's amplitude decreases, the modulator output frequency decreases. So modulator output frequency is in its maximum when the message signal reaches its peak positive peak value. When the message signal reaches its negative peak value, the output frequency of the modulator is minimum. FM technique is mostly used by the FM radio stations, FM radio stations use this method because of its quality signal receiving at the demodulator site. When we give modulator output to the demodulator, output is seen as same as in frequency as with the message signal. Because of input information is carried out by the frequency, not by the amplitude. So we got the input information at the demodulator output. PLL FM demodulators are widely used by the most of the radio stations, ranging from broadcast stations to the high performance communication equipments. Nowadays, PLL FM demodulators are used by most of the radio stations because it is the most efficient way of demodulating a signal. So with this, we concluded the video of our simulation part. Thank you.